Hello everyone, this is a video abstract on my paper on genus one curves violating the local global principle. Let me introduce the background first. Let X be a nice variety. Nice means smooth, projective, and geometrically connected, divided over a number field K. Let omega K be the set of all non-triple places of K. Kv be the combination of K at a place V. We say that X violates the local global principle if the local point xkv is non-empty for every v, whereas the rational point xk is empty. By experience, in a given algebraic family of varieties over a number field, finding a counterexample to the local global principle is akin to finding a needle in a haystack. There are some known cases. By the Hasse-Minkowski theory, every nice curve of genus 0 satisfies the local global principle. The first nice genus 1 curve, discovered by Linda and Richard, violates the local global principle. And this genus 1 curve is the smooth projective model divided by this equation. And the well-known semi-cubic curve, this one, it also violates the local global principle. Fulham proved that for each number field K, there is a nice curve divided over this field, violating the local global principle. Clark proved that for each integer G greater or equal than 2, and each number field K, there is a curve C over this over the number field K of genus G, violating the local global principle. So the rest of the K for curve is genus 1 curve, and Clark put a conjecture. For each number field K, there is a nice curve, nice genus 1 curve, violating the local global principle. Our paper is to prove Clark's conjecture holds for a number field not containing Qi. Here, I is the square root of -1. Our way to prove this conjecture is given an explicit construction. We consider curves divided by the equation Qy squared equals the fourth power of x minus p. Here, PQ is the integers in K. We need to choose the parameters PQ in K such that the curve given by this equation violating the local global principle. It is easy to make sure the curves having local points, but to make sure these curves having no K rational point is difficult. The below-many obstruction, in some cases, can give a criteria to judge whether these curves have no K rational point. We briefly introduce the below-many obstruction below. Like an element A belongs to the Brouwer group of X, consider the following commutative diagram. The K rational points of xk. This is the other points of x. And this is the Brouwer group of K. This is the direct sum of the Brouwer group of Kv. This is the sum of local invariants. By the Brouwer-Hasse-Rotter theory, the last law is exact. Then we can divide this set xak equals to the other points satisfy this condition. The sum of invariants is equal to 0. And by this commutative diagram and the Brouwer-Hasse-Rotter theory, the K rational point set is contained in this set for any A. And in particular, if this set is empty, and then this set is empty. Back to the proof of our theory. we consider the curve divided by this equation. And it is well known this curve is of genus 1. And we consider quaternion algebraic class A equals yp. This element belongs to the Brouwer group of the function field of this curve, and is indeed belonging to the Brouwer C. And this is also a two-torsion element. Using this element, and we divide this set and choose the parameters PQ to make sure this set is empty. Then we have our theory. For any number field K not containing Qi, there exists a genus 1 curve C divided over this field, violating the local global principle. And from this curve, we know this curve has a zero cycle of degree 2. And the geometry of this curve, we have the following query. For number field K not containing Qi, there exists an elliptic curve E divided over K, such that the two-torsion subgroup of subunit group of E is non-trivial. Although by now we can prove this theory for any number field, but we still want to know what this kind of curve, the curve divided by this equation, can answer this question. Okay, thank you.